Aloha! In this short lecture, we'll discuss the autoionization of water. Water undergoes what's described as a self-ionization process, meaning water molecules have the ability to produce ions, and the way they do that is by splitting apart into ions. So here's a water molecule, and it can split apart into a proton and a hydroxide ion. So every water molecule has the ability to do this, and they do. They're constantly doing this. In fact, any bulk water that you come across, there's an equilibrium that's occurring between the undissociated water molecules and the dissociated ions. So it's an equilibrium. Now, this equilibrium is constantly occurring in all aqueous solutions, including pure water. So it's not just pure water which is doing this, but anytime there's bulk water around. So even if there are other things dissolved in the water, if it's an aqueous solution, the background water is constantly doing this. Like any equilibrium chemical equation, we can write the corresponding equilibrium constant expression for it. So here we go. The equilibrium constant, we'll give it a subscript W since we're talking about water here. So Kw is equal to the product concentrations over the reactant concentrations. So here it's equal to the proton times hydroxide concentration. And the reactant is a pure liquid. So remember, you don't have to include pure liquids and pure solids. It would be like you're dividing by 1. So the equilibrium constant expression for this equilibrium is pretty simple. It's just the proton times the hydroxide concentration. And at 25 degrees, the equilibrium constant is 1 times 10 to the minus 14, or simply 10 to the minus 14. If it is pure water, then every time a molecule splits apart, there would be a proton and a hydroxide ion. And therefore, that means that the number of protons will always equal the number of hydroxides because they each came from a water molecule. So in pure water, the two concentrations happen to be equal, and they're equal to 1 times 10 to the minus 7, or simply 10 to the minus 7 molarity. Because if the product of the two concentrations equals 10 to the minus 14, and those concentrations are equal, then that means they both must be 10 to the minus 7. So since the concentrations are equal in pure water, we call that neutral. If a solution happens to have more proton than hydroxide concentrations, we call that acidic. The way you get that is by taking pure water and dumping in an acid. So if it's pure water, the concentrations are equal, but as soon as you dump in an acid, you're giving it extra proton concentration. And so what happens is the proton concentration goes up, but the hydroxide concentration would end up going down because the product of those two concentrations must still equal 10 to the minus 14. So if you dump in extra proton, then the hydroxide concentration decreases. So solutions with more proton than hydroxide are acidic, and vice versa. If the hydroxide concentration is greater than proton concentration, we describe those as being basic. Now, this relation right here is very important because it allows us to see how the proton and hydroxide concentrations are related to each other. If you know one, then that means you know the other one. So in certain solutions, it's easy to figure out what the proton concentration is, and therefore you can use this equation to calculate the hydroxide concentration, and vice versa. In acids, we usually can get to the proton concentration pretty easily, and therefore we can calculate the hydroxide concentration. And if we're dealing with bases, then we can figure out what the hydroxide concentration is without too much trouble, and therefore calculate the proton concentration. Let's do a couple of examples of this. Here's one. Suppose you're asked to determine the proton concentration, the hydroxide concentration, the pH, and the pOH of 0.0005 molarity HNO3. You should recognize HNO3 as one of the 6 strong acids. So this is a strong acid, and like all strong acids do, it dissociates completely in solution. So if you have a solution which is 0.0005 molarity nitric acid, then it all dissociates and you end up with 0.0005 molarity of protons and 0.0005 molarity of the nitrate anions. But here's your proton concentration. Now, this proton concentration dominates what water provides. So water provides 10 to the minus 7 molarity by itself, but in this solution, there's so much proton there that you can ignore what water is contributing. So you have the proton concentration, and using the equilibrium constant expression that we saw above, we can calculate the hydroxide concentration. I'll remind you one more time. The two concentrations multiply to give 1 times 10 to the minus 14. So to get the hydroxide concentration, it's equal to 1 times 10 to the minus 14 over the proton concentration. So you plug in the proton concentration, and when you do the calculation, you get 2 times 10 to the minus 11. So you see your proton concentration is now much bigger than 10 to the minus 7 because it's an acid we're talking about, and therefore the hydroxide concentration has dropped to much lower than 10 to the minus 7. But these two will still multiply together to give 10 to the minus 14, and you can check that. Since we have the two concentrations, we can calculate the pH and the pOH. The pH is the negative log of the proton concentration, so you plug that in and you get 3.30. And the pOH is similarly calculated. It's the negative log of the hydroxide concentration, and that equals 10.70. Now there is an easier way to get the pOH. Once you know the pH, there's a much quicker way to get the pOH. Notice that these two add together to give 14. That's not a coincidence just for this solution. In fact, that occurs in every aqueous solution at 25 Celsius. The pH plus the pOH will equal 14 at 25 Celsius. Now this equation right here is derived from, follow the pink line, from that equation. The two are the same thing. So I don't know if you can see them both, but here we go. The two concentrations multiply to give 10 to the minus 14. We can use that to get pH plus pOH equals 14. So let's do that. Let's start with the above equation. The proton times the hydroxide concentration is 10 to the minus 14. If we take the log of both sides of this, we get log of the proton times hydroxide equals the log of 10 to the minus 14. Now the log of 10 to the minus 14 is just minus 14. These are inverse operations. So the log and the base 10 cancel each other, and you're just left with the exponent. And the log of a product equals the log of the one plus the log of the other. So we're getting there. If we multiply both sides by -1, this turns into 14, and those turn into negative log proton minus log hydroxide. Negative log of proton concentration is pH, and minus log hydroxide concentration is pOH. And so pH plus pOH equals 14. So we could have used this to calculate the pOH above. Once we know that this is 3.30, the other one has to be 10.70, because that's what it is to get 14. Let's do one more example involving a base. We'll talk more about bases in the next video, but here's a quick example. suppose you're asked to find the pH of 0.0073 molarity sodium hydroxide. Now this is an Arrhenius base because when it's dissolved in water, and you can see its aqueous solution, like all ionic compounds do, it fully dissociates in water. So ionic compounds, when they're in solution, they're dissociated. And so the sodium hydroxide will completely dissociate into sodium pluses and hydroxide minuses. And there you go. You have hydroxides in solution, and that's what a base is. If you're starting with 0.0073 molarity of the ionic compound in solution and it fully dissociates, that means you have 0.0073 molarity of the sodium pluses and also the same molarity of the hydroxide minuses. Now, as the acid dominated the proton concentration, this one will dominate the hydroxide concentration. You can ignore the hydroxide that water produces. It's only 10 to the minus 7 molarity. When you're dealing with this solution, that's way more, and what water contributes is insignificant. So here is your hydroxide concentration. What you should do at this point is to use it to calculate the pOH, and that is 2.14. And once you have the pOH, you know that the pH is whatever it takes to get 14. So 2.14 plus 11.86 would equal 14. So the pH is 11.86. So that's an easy way to solve that one. One last thing before we end this video, just a little more detail on the pH scale. Okay, the pH scale, here it is up at the top. It ranges from about 0-ish or so up to about 14, although you can go a little bit higher, you can go a little bit lower. So here is the pH from 1 to 14. Now, we saw in a previous video that when a solution is pH 1, then that's the same thing as the proton concentration being 10 to the minus 1. If the proton concentration is 1/10 of that, so 10 to the minus 2, 1/100th, this is 1/10, this is 1/100th, then that means the pH is 2. If the proton concentration is 1,000th, the pH is 3, and you can keep on carrying this all the way down. When the proton concentration is 10 to the minus 14, the pH is 14. With the autoionization of water, we know that when the pH is 7, that means the proton concentration is 10 to the minus 7, and the hydroxide concentration equals it. And the pOH would be equal to 7. When the pH is 6, the pOH has to equal 8, right? Because the two always add together to give you 14. So you can see the relation between the pH and the pOH. So when the pH gets lower, the proton concentration increases, but the hydroxide concentration correspondingly decreases. And this pink region right here is the region where there is more proton than hydroxide, and the pH is lower than the pOH. And the blue region is where the pH is high, and the pOH gets low. There's more hydroxide concentration than proton concentration. So this would be a good scale to memorize. Really, you just need to know the pH scale. 7 is neutral, less than 7 is acidic, greater than 7 is basic. But you should also know the relation between the pH, the H plus concentration, the OH minus concentration, and the pOH. If I were you, I would memorize this whole scale. In our next video, we will get into bases in a little more detail, and we'll discuss the difference between strong and weak bases. So stay tuned for that. Aloha.